Hello everyone. Welcome to this fantastic journey through the world of machine learning. In this video we will explore decision trees, powerful and widely used machine learning algorithms that provide a graphical representation of decision-making processes. We will delve into the algorithm process, its advantages and disadvantages, and explore its derivatives. In the video description, you'll find links to related videos and playlists on today's topic. I invite you to take a look because there is further information or insights that could interest you. If you'll find in this video concepts or topics that you didn't fully grasp, you can look in the description for additional explanations and helpful resources. I understand that some ideas or concepts might seem complex, but I'm here to simplify and make these topics accessible. If you don't understand something, please ask in the comments. Before we begin, I'd like to ask, if you haven't already, to subscribe to my channel. Decision trees are powerful and widely used machine learning algorithms that provide a graphical representation of decision-making processes. They can be applied to both classification and regression tasks. A decision tree is a flowchart-like structure in which internal nodes represent features, branches represent decisions, and leaf nodes represent the predictions. In the case of classification tasks, each leaf node corresponds to a specific class label, and the majority class in a leaf node is assigned as the prediction. For regression tasks, the leaf nodes represent continuous values, usually the mean or median of the target variable in that leaf. The functioning of decision trees involves a step-by-step process of splitting the dataset based on selected features. This creates a tree-like structure that enables effective predictions. The algorithm can be summarized as follows. Start with the entire dataset as the root node of the decision tree. Select the most informative feature that best separates the data points. The feature selection is based on criteria such as Gini impurity or information gain, which measure the impurity or uncertainty within subsets of data. Split the dataset into subsets based on the possible values of the selected feature, creating internal nodes and branches. Repeat the feature selection and splitting process for each subset, considering only the remaining features that have not been used yet. Continue recursively splitting the subsets until a stopping criterion is met, such as reaching a maximum depth or achieving a specific level of purity. Assign the majority class or the mean value of the target variable to each leaf node. Decision trees offer several advantages. Interpretability. Decision trees offer a clear and intuitive graphical representation, making them highly interpretable and providing insights into the decision-making process. Handling mixed data. Decision trees can effectively handle both numerical and categorical data. Numerical data obviously represents information that have a numerical meaning, while categorical data represents information that does not have a natural numerical meaning, for example the color or the type of a car. Robustness to outliers. Outliers are extreme values that deviate significantly from the majority of the dataset, often caused by measurement errors or anomalies. By focusing on important features, decision trees can generate reliable predictions even in the presence of outliers. However, if the dataset contains a large number of outliers, decision trees may not perform optimally. In such cases, preprocessing the data may be necessary. Low dependency on domain specifics. Decision trees can be applied to a wide range of problem domains without requiring deep domain expertise. This characteristic is advantageous as it enables decision trees to handle datasets where the importance of features may vary across different problems, also reducing the need for manual feature selection. However, decision trees also comes with possible downsides. Overfitting. Decision trees can be prone to overfitting, particularly when the tree becomes overly complex or when the dataset has noisy or imbalanced classes, a situation where a label has significantly more instances than the other labels. High variance. Decision trees can exhibit high variance, meaning that small changes in the training data can result in significantly different trees and predictions. This sensitivity to small variations can cause the model to overfit the training data and perform poorly on new data. Techniques like tree pruning and regularization help mitigate high variance and improve generalization. Difficulty with complex correlations. Decision trees struggle with capturing complex correlations between features since they make independent decisions at each split node. Lack of global optimality. Decision trees optimize locally at each node, making decisions based only on the information available at that specific node, risking not considering the full range of possible splits and optimal solutions globally. To mitigate this issue, techniques such as boosting algorithms and cascade decision trees have been developed. Decision trees have given rise to various derivatives that aim to enhance their performance or address specific challenges. Random forests employ an ensemble of decision trees trained in parallel to improve predictive accuracy. By combining the predictions of multiple decision trees, random forests can reduce overfitting and provide more robust predictions. Gradient-boosted trees, also known as GBMs or gradient boosting machines, sequentially train decision trees to minimize the prediction error. Each subsequent decision tree in the ensemble corrects the errors made by the previous trees, leading to increasingly accurate predictions. In summary, decision trees are valuable tools in machine learning. They consist in a step-by-step process that creates a flowchart-like structure by recursively splitting the dataset based on most informative features. Decision trees offer interpretability, versatility in handling different data types, robustness to outliers, and low dependency on domain specifics. However, they should be used with caution to avoid overfitting and to consider possible high variance, their limitations in capturing complex correlations, and lack of global optimality. Derivatives of decision trees include random forests that utilize an ensemble of decision trees and gradient-boosted trees that iteratively train decision trees to minimize prediction errors, with subsequent trees correcting the errors made by previous trees. And that brings us to the end of today's video. Thank you so much for watching and being a part of this journey. I truly appreciate your support. Don't hesitate to engage with me through the comments. I love hearing your thoughts, questions, and suggestions. Your input helps me tailor my content to your needs and interests. Leaving a like, sharing the videos, or commenting can make a huge difference. If you haven't already, please consider subscribing to my channel. It's a simple gesture, but it means a world to me. There is a lot of effort behind each video. I put in all my dedication to try and create interesting and to the point content. If you click on the subscribe button, I can go on creating for you, free and quality service. Thank you once again for being here, and I look forward to seeing you in the next video.